Hello everyone. Today we're looking at measuring and classifying angles. We had been looking at points, lines, and planes and all of the notation we would use in reading diagrams. Now we're taking those objects we called rays and bringing them together to create a new object, the angle. So we will be measuring them, we will be classifying the angles, and so we have a lot of vocabulary to introduce here. Much of this is stuff you've seen before in your middle school math classes, but here we are still in our first unit. We're introducing all of the basics of geometry and the specific notation that we need. So there's a lot of detail we have to review, and that's what we're going to look at doing today. So once again, we have the definition on the left column, and we'll add in the geometric figure and the notation on the right. So let's start off with the angle. The angle consists of two different rays with the same endpoint, where the sides of an angle are the rays. So again, the sides of the angle are the rays. And the endpoint of the angle is called the vertex. So here is my first ray. Again, we need two different rays, so let's bring in a second, and we're going to line up the endpoints of those rays so that they are touching each other right there. And so we need to give this a name, so it is a point. We give it a capital letter. And if we have a ray, we have to have 2 points as well on that ray. So this is the side of the angle, which is a ray. So this is ray AB. Remember, you start with the endpoint and you name the ray passing through the point. Here we have ray AC, so let's add on a point C on that second ray. So just to label some of these things, this is the vertex, sort of where the point of the angle is, or where the two rays come together. That's the vertex. And then these are the sides of the angle. So the sides are rays. Alright, so when we are naming an angle, we are going to use the name of the vertex. In this case, we have a capital A. So we would call this angle A. We use a little miniature angle symbol right in front of the capital letter. Or we can use a 3-letter combination, and the letter of the vertex must always be in the middle. So we could call this angle CAB. So the letter C is on one side of the angle, the letter B is on the other side of the angle, and the vertex is smack dab in the middle. So it's like you're starting at C and kind of working your way around those 3 letters. So angle CAB. Or we can go in reverse order. We can call it angle BAC. Now sometimes when we have lots of angles in a big diagram, we might number the angles off, and so if I were to call this angle 3, we would put a little tiny 3 inside. This is not 3 degrees, it's not a measurement, but it's just another way to name an angle, and that's more useful when we have lots of angles all at once. We've used our slice of pizza before when talking about points on a plane. Here I'm using the slice of pizza to talk about not the plane, but the angle. So you can see how we have one slice of the pizza, one side of the pizza slice, the other side of the pizza slice come together. There's your vertex, and there's the angle. Right. So let's classify these different types of angles. We have small, medium, and large type angles. The smallest is the acute. An acute angle is an angle whose measures between 0 degrees and 90 degrees. So it has to be bigger than 0, less than 90. It has to be between those two. So this diagram will look very similar to the previous one. Here are my 2 rays. And I'll call this vertex A. So this is angle CAB. Or we could just call it angle A. And let's say we are describing this as having a measurement of 50 degrees. So notice the difference between these two diagrams. When I labeled the 3 inside, there was no degree symbol. So we know that's just the name of the angle, angle 3. Here, because of the degree symbol, we know this is its size, its measure. So to describe that measure, that angle A has a measurement of 50 degrees, we then put a little m in front of the angle symbol, which is in front of the letter of the vertex. So we say the measure of angle A equals 50 degrees. That's between 0 and 90, so that's an example of an acute angle. Here we have a right angle. A right angle has a measure of exactly 90 degrees. I'll use the same letter, so angle A at the vertex. Now in our diagrams, the way we symbolize that is we don't write down 90 degrees, we put this little box, and it's often in red. You'll see in the textbook they use a little red box there as well. So here we would say the measure of angle A equals 90 degrees. It's not wrong to put the number 90 degrees here inside the diagram, but we just symbolize that with the box instead. Our obtuse angle then is an angle that is bigger than 90 degrees, but less than 180. So we say between 90 and 180 degrees. So I'm naming this angle the same. And let me pick, how about 120 degrees? So here we would say the measure of angle A is 120 degrees. In these right-hand columns, and thinking about some illustrations, for the right angle, we see this all the time in math when we are dealing with our XY axis. When we're talking about our Cartesian coordinate grid system, we always have a horizontal axis, we call the x-axis, and a vertical, we call the y-axis, and they happen to be perpendicular to each other, which forms a right angle. So that's a common example you see all the time. Maybe you look outside and there's your ground and you happen to see a tree and there's the tree standing up straight. That tree would be thought to be at a right angle with the ground. So let's use the tree for these acute and obtuse examples. Let's say a windstorm came along and sort of blew that tree over a bit, so it's leaning quite a bit. And so on the smaller side, this angle on the right here would be our acute angle. And if we use that exact same diagram to describe an example with the obtuse angle, well, here's our leaning tree. And this time we're using the left-hand side. That's the bigger angle. That's the angle that's bigger than 90 degrees. So there's your obtuse angle. We're going to come back to this illustration of the leaning tree in just a moment when we're talking about a straight angle. Right? So a straight angle is the biggest still. We've had our acute angle, which is less than 90, the right angle, which is exactly 90, an obtuse angle is more than 90, but less than 180 degrees. And if we have an angle that is exactly 180 degrees, well, something very curious happens. Here's my first ray. And if we were to take a moment and look at the diagram above where we have the obtuse angle, if we take this left-handed side, this left angle, this left ray, and we reposition it so that the space inside is not 120 but 180 degrees, what we're going to find is that this side of the angle is going to be pointed in the exact opposite direction as the other ray. So we have, it looks like just a straight line. So the sides of the angle have opened up so far that they are pointing in opposite directions. We have an example of two opposite rays, and they form a straight line, and we have exactly 180 degrees. Sometimes a little arrow symbol like that will help to kind of illustrate, hey, we're talking about this size. That's our 180 degree. So it looks a little bit odd to call it an angle because it looks like a line, but in fact a line has 180 degrees on its side. So for the illustration, think of that tree that has been blown in the windstorm, and let's just say that it's got blown completely down. So there's the tree lying on the ground. There's your straight angle. So those are the classifications of those types. So now we're taking it one step farther. We're going to take an angle and we're going to put a ray inside that angle. So now we have not just 2 rays but 3. Alright, I'm going to use the obtuse angle here. So we have a bit more space inside. Here is my angle A. And what we're going to do is we are going to bisect the angle. So we had bisected a segment before, and that meant to cut the segment in half. Here we're going to bisect the angle, and that means we're going to cut the angle in half. So we need a new ray. Let's take a ray that divides this angle into 2 angles that are congruent. That means they have to be the same size. So here is a third ray, and we'll just eyeball where we think it ought to go, somewhere in the middle here. So let's call this ray AD. And because it's cutting the large angle into 2 congruent angles, that means these have to be the same size. So we use arcs to symbolize that these 2 are the same size. Now when you draw these arcs, slightly offset them, stagger them a little bit, so it doesn't look like one continuous arc. We want to break it up. But we have a single arc on the left, a single arc on the right, so we know these 2 angles are the same size. So let's write this down. Ray AD, there's my ray symbol, is the angle bisector. So ray AD is the angle bisector of the big angle, but I can't just call it angle A because we have lots of angles now. So this is angle CAB. The original angle is the big angle, angle CAB. So we're saying this ray AD is the angle bisector, meaning it is cutting in half this big angle, angle CAB. What that means is we now have 2 smaller angles, but they are the same size to each other. They are congruent. So we would say angle CAD on the left is congruent with angle BAD on the right. Again, when naming angles, you can name those 3 letters forwards or backwards. It doesn't really matter. Now we don't have any numbers to suggest the size of the angles, which is why we use the word congruent. But if we did take the measure, well, it would make sense that the measurement would be exactly the same. So if we have angles that are congruent, it makes sense that they should also have the same measure. But our notation changes. So take a closer look at how we're going to change our notation from congruency to equality. So again, when we use the congruent sign, we use that when we have no numbers, or the emphasis is on the fact that they're the same size without relying on the numbers themselves. But if we do have numbers, then we will use the equal sign. But if we have numbers, then that means we have to put the M in front of the angle symbol to represent we have a measurement. So we would say the measure of angle CAD equals the measure of angle BAD. So it's a lot of writing with all these little symbols, but that's how we communicate 2 angles that are equal in measurement versus 2 angles that are congruent. So I need to make a little bit of a highlight here, a little bit of a note. Watch out for this. I'll say recall. I don't know that we've actually talked about this, but something to keep in mind regarding our vocabulary with segments versus angles. So recall that when we are talking about segments and how we describe them, we do not say segments have measure. No, we say segments have length. That's their characteristic. But angles don't have length. No, angles have measure. And so this is how we pair up the vocabulary. Angles don't have length. No, angles have measure. In the same way, segments don't have measure. Segments have length. So length is the quality of segments, and measure is the quality of angle. So that's how the vocabulary are paired up with those two. Okay, example 1, let's name the three angles in the diagram. So you'll see that we have, first of all, our big angle. So I'm going to outline them here so it kind of stands out a little bit. So this is the big angle. Here's one side. Here's the other side. So this is angle ABD. Alright, so angle ABD, or backwards, angle DBA. But then we also have these smaller angles inside. So here now we have, sort of on the top half if you will, this is angle ABC. Or backwards, angle CBA. And then the third angle is on the bottom half, if you think of that as the bottom half. There's the third angle. So this is angle CBD. Angle CBD, or backwards, angle DBC. That's how we would name them with their letters. Again, it's possible that we could have numbers inside. We might call this, for example, a little 1 and a little 2. So on the top half there, if we had numbers, we could call that angle 1. And then on the bottom half there, angle 2. The diagram didn't come with numbers, but sometimes you'll see them labeled in that way. In an instance like this, we often don't put a number then for the biggest angle there. Notice that in all of these cases, we should not name any of them just angle B. If you remember, when we first introduced angles to you, we said that you could name an angle using just its vertex, in this illustration calling angle A enough. But we cannot do that in every case, because if you just call it angle B, we don't know if we're talking about the top angle or the bottom angle or the big angle, because they all share a common vertex. So if you just call it angle B, it's not specific enough. We don't know what angle you're talking about. So if there's multiple angles sharing the same vertex, you have to use the three-letter combination. Alright, so that's the names and the classifications. We're going to now take some measurements, and we do that using a protractor. So if you look at the next page, here at the top we have a protractor that's printed, and most likely you may have seen these before. Here's one in the hand. It has a ruler or a straight edge on the bottom, and then on the top is a half a circle, and so this allows us to measure the size of an angle. So wherever the side of the angle passes through, then that tells you how many degrees we have. But there's two scales. There's an outer scale and an inner scale. So we would always use the scale that starts at 0 and count upwards. So 0, 10, 20, 30, 40, 50 degrees. If I were using the outer scale, I would actually start over here on the left-hand side. 0, 10, 20, 30, 40, 50 degrees. So most often, and I'm jumping ahead a little bit here, if I were to look at this diagram and I were to say, I need to measure this angle, well, the first thing we might want to do is just extend the sides a little bit to make it easier to measure with our protractor. So I'm just making that a little bit longer. And then when we want to use our protractor to measure the size of this, we need to line up one side of the angle with the straight edge of the protractor. And this little guide hole that you see right there in the middle, that's where the vertex goes. So we're going to place that little guide hole on the vertex, and then we can pivot the protractor back and forth until we have one side of the angle lined up with the straight edge. We could also do it this way. Again, there's the guide hole. We could place that at the vertex, and then we could just kind of line up so that this side of the angle lines up with the straight edge, and we want it to go right there through 0 degrees. So then that means this side of the angle would extend to way out here. And so I want to start at the 0 and count upwards. If I use the inside track, I'm counting downwards with 170, 160, 150, and so on. Let's start on the outside track and count upwards. So there's 0, 10, 20, 30, 40. Keep on going. There's 90 degrees. Keep on going. 100, 110, 120, maybe 130 degrees is what we would have. So that's commonly how you would measure using a protractor in your hand. But in the case where it's already printed on the page, I don't have the luxury of turning it around, and that means if I want to take a measurement, I have to do a subtraction problem. I have to subtract the number of degrees to find the difference between them. So let's illustrate that. We're going to use the diagram to find the measure of the indicated angle, and then we'll classify the angle. Let's identify angle WSR. Alright, so there's W, there's S, and there's R. So we're looking at this right here. Now, because this side of the angle does in fact go through 0, then we can just count upwards on that outer track. So 0, 10, 20, 30, 40, 50, 60, looks like 65 degrees. So we would say the measure of angle WSR is 65 degrees. Well, that's less than 90, so that would be an acute angle. In part B, we have angle TSW. TSW. Well, T again is on a side of an angle that does go through the 0 on the inner track. So again, we can just count upwards. 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 115. So the measure of angle TSW is 115. That's bigger than 90, so that's our obtuse angle. When we're looking at the measure of angle RST, here's R, here's S, here's T. Both sides are lined up with the straight edge of the protractor, which means that that's a straight line. That's 180 degrees. And if you started here at 0 and you counted on the outside track, you'd get all the way up to 180. Or if you started on the right-hand side at 0, on the inside track you would count 0, 10, 20, 30, 40, 50, and keep on going all the way up to 180. So either way, you would get exactly 180 degrees. So the measure of angle RST is 180. That's a straight angle. Here in part D, we have the measure of angle VST. So there's VST. So again, the side with T is crossing through the 0 mark on the scale. So VST, those look like perpendicular lines. Looking at the inside track, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, it is a right angle. So the measure of angle VST equals 90, and that is a right angle. So I wanted to add one more. Let's look at example E. What if we were looking at this angle that is between the sides of W and V? Because now neither of these sides of this angle go through the 0. Neither of these sides line up with the straight part of the protractor. So if I want to identify the size of this angle, we should do a subtraction problem. So let's take a look at the outside track for an example. The right side of this ray passes through 90 degrees, and the left side of the ray, right here, passes through 65 degrees. So we would have to do a subtraction problem to find that. So this is angle VSW. The measure of angle VSW, VSW equals, and we would think in our heads a subtraction of 90 degrees minus 65 degrees. Alright. Technically, we could count even. If you count by tens, you could go 10 degrees, 20 degrees, 25 degrees. And that would be an acute angle. So there are a variety of different ways of calculating the size of the angle using that protractor. Here in example 3, we are returning back to just practicing naming the angles in the diagram. If we were in class, I would call on you to help out. So you might pause the video here, name the 3 angles in the diagram, and then once you have your names written down, come back and check the answers. So let's see what we have Here we have sort of on this top angle, or on the left hand side, we have F, G, and J. So this is angle F, G, and J. Now again, remember you can name it forwards or backwards. So you could have called it angle JGF, but do not call it angle G because we have too many angles that share the same vertex. Here on the right hand side we have angle JGH, or backwards, angle HGJ, and then the biggest angle goes through letters F, G, and H, or backwards, angle HGF. There's your answer. We've already talked about this here. Example 4, it says, what type of angle do the x-axis and the y-axis form in the coordinate plane? We've already talked about this as the illustration for our right angle. So oftentimes you're graphing and use the x-y axis system, and there is our right angle. Alright, a couple more vocabulary words. Let's take a look at parallel and perpendicular lines. They also have their own symbols to keep in mind here. Here, if we're talking about parallel lines, these are lines that do not intersect and are coplanar. You might not think of that as being necessary to describe parallel lines. But let's start off by drawing a line. Remember, a line has to have arrows on both ends. We have a line, so we should name it. I'll use lowercase, sort of italicized letters. So there's line L, there's line M. Now for symbols, we want to communicate that the diagram shows that the lines are parallel, and we do that with little arrows that are inside. And again, usually the book will use red to show that information. So you don't look at the arrows on the ends, no, you look at the arrows in the middle. So we can use single arrows, we could even double them up and use double arrows, we could use triple arrows. As long as they match, that means those two lines would be parallel. So we would say line L is parallel with line M. So that parallel symbol looks like a real tall, skinny 11. It's not the number 11. It means we have two lines that are parallel to each other. Segments could also be parallel to each other, but here we're talking about lines, so we drew lines. We're talking about perpendicular lines. If two lines intersect to form a 90-degree angle, then they are perpendicular lines. And this is the same idea, but in reverse. If any two lines are perpendicular lines, then they intersect to form a right angle. And we've been looking at this recently with our xy axis on the coordinate plane. So here we have line L, here we have line M. Again, the way we show that symbol is with that little box. Now that box means that they are right angles. And if we have a right angle, then we know that the lines are perpendicular to each other. So we would say line L is perpendicular to line M. So that symbol looks like an upside down capital T, but really it's just a miniature vertical and horizontal bar to suggest that they are perpendicular to each other. Let's finish off with this bisecting an angle. This is not a formal construction. We'll do that in our next lesson. But let's take an angle on a scrap of paper and bisect it without actually taking any measurements. These are the steps walking you through it, but I'll just demonstrate it here. Here's our vertex at B, and so I have A and C on the left. So there's A, B, C. All we're going to do is just fold the paper, and we're going to fold it in such a way that we want the crease to go right through the vertex, and we want to make sure that the two rays overlap each other. So I'm going to position the rays so that one is lined on top of the other. So where that crease occurs, that is the angle bisector. We said there is now a third angle that goes right through the vertex, and that is creating two angles that are exactly the same size. So we use those arcs, slightly offset them, slightly stagger them, And that's the concept right there. So I'm just going to take that and symbolize it with its own diagram here, just kind of sketch out what we did. There's my angle. And so we folded the paper so that ray BC was on top of the other side, ray BA. And then what we found was we came up with a crease. And then where that crease occurred, that was our angle bisector. And where that crease occurred, we then drew in a solid line, or a ray rather, and we put point D on that, so that we then knew that those two angles were congruent. And that's it for this lesson. Next lesson we'll continue on with our concept of angles and bisectors. We'll set up equations and solve for missing angles.